So we have the next speaker. We have now Dr. Thomas Avoidance. Since November 2015, Dr. Avoidance is the co-CEO and co-founder of Engineering Data Intelligence, which is a spin-off of the Karlsruhe Institute of Technology. He has been working in the field of automotive technology since 2008, especially in the field of novel methods and tools for developing and testing. As a member of the research team in the Institute of Product Engineering Karlsruhe at KIT, he is focused on innovative technologies such as electric vehicles, autonomous vehicles, and artificial intelligence. So thank you very much, Dr. Freudemann, and welcome.
Yes, thank you very much for this nice introduction. Welcome to my presentation about the dynamic risk management algorithm. And I will present today for how we developed this algorithm, for what is it good, and yeah, also the different use cases where you can use it. And overall, for sure, we want to make the driving and navigation more safer, and also we want to have it accepted from the driver and from the passenger, also in the autonomous driving. And my name is Thomas Freudemann. I'm the CEO of the EDI, Engineering Data Intelligence. So we are also a spin-off from the KIT, founded 5 years ago. We are located in Karlsruhe. So this is why I also now here at the nice PTV room. So that's really nice. And also PTV is a spin-off from the KIT. So I think 40 years ago. So we have some way far in front of us, but we will keep going here on, and also with autonomous driving stuff. So the main reason for accident, for sure, it's not right approach speed, and sometimes it's your fault because you are too fast in some driving situations, but also the opponents, other traffic opponents, are sometimes the reason why you have not the right speed. And that's really what we want to focus on with our dynamic risk management algorithm. It's about driving context and also about the expectation of the other opponent's behavior. And our approach based on a safety cushion approach, that means in general you need space to brake so that situation get not critical. And you know, also today we hear from Mr. Lohmiller that it's really important to also keep this line changing in mind, because also then you can sometimes avoid some critical situations. So it's about safety cushion in a longitudinal way, but also in a lateral way. So we have to keep this in mind. And on this, our approach, yeah, it's the fundamental of our approach. We were lucky because here you can see a video where you can see this opponent who was crossing the street. So it suddenly appeared. And these are videos, and we have more than 100,000 of this kind of incidents where, for example, taxis in Tokyo has to brake because something happens. And then we get 15 seconds of this kind of videos. We get some signals from the car. It's about the speed, it's about acceleration, but also if he used the brake pedal and so on. So that's our conventional car. So we not have radar and other signals. But we get this speed information from the car, and what this database makes it really powerful, and it's the big advantage of this database. All these 100,000 incidents were labeled manual from experts. So there's a label list with more than 100 labels where we get additional information about this situation. So this project was starting 10 years ago. So today, there would be more artificial intelligence in place, but in this time we have a lot of manual work, and that makes it also powerful because also these experts are ranking all the incidents on 5 levels. So there could be an accident, high, medium, low, or there was nothing, and that helps us really to train our models. And that is what we exactly were doing. So we work together here since more than 4 years with 2 universities out Japan, where also this database is located, and also OEMs out Japan to train this algorithm. And on the right side, you can see the algorithm. We keep different context parameter in mind. So that's more than 100 context parameter which we have in mind. But also we have a driver behavior model behind. That means in a certain situation, we can calculate what would be the right speed to reach a certain level from the incident. So the incident level, you can imagine it's like a risk score. So, and you know already, so there are some drivers which are maybe more risky, so it goes more to the red line, but there are also some drivers who are really safe or want to drive really safe, so it goes more to the 20 area, so the yellow bar. And you understand already here, it's a driver model which we can adjust to the behavior and the wishes of the driver. So that is about driver acceptance. And also, this is why I'm also make the presentation here today, because we were also using the PTV Visim environment to validate our algorithm. If we trained the algorithm with the realistic data, but to validate, we were using this simulation data from the traffic, from a realistic traffic flow simulation from PTV Visim. And in our case, the driver context friendly driver was our DRM car. And in this case, the bad driver from PTV. So because he not keep care about the driving context, the PTV driver only keep care about some generic speed controls. So maybe 50 km/h in the city. And we connect our algorithm over a DLL interface. It's a standard interface from PTV Visim. And so we could use our driver model directly in the PTV Visim simulation, and that works really good. And here I will show, so we also bring in from the information from the 100,000 incidents, we also make the right spawn rate of the pedestrian with the right speed. So we try to get the same behavior like we get in the real data. So that we bring in the simulation. And here you can see a simulation where some pedestrians are crossing the street. Sometimes it's really close. Sometimes you have more space. And that is what also happens in the reality. So at the end of the day, we simulate 24 hours, different traffic situations. And we also develop, I will say, a tool to evaluate in an automatic way each of these incidents, because as in reality, sometimes the pedestrian and the cars are far away, so nothing happens, but sometimes they are really close because the pedestrians are dashing out. And with this algorithm, so that means if the yellow box is over the yellow box, we have a medium incident, because the time where the people were together, it's in these yellow boxes. So in this way we could calculate automatically the incident levels. And it's the same like we have in the reality. So also the behavior on the right side, you could see the behavior of the PTV car, and you can also see here these guys are braking. So that is the same behavior we also see in the reality. And also we have some approaches to avoid this kind of incidents. Yeah, you can make a small line change, you can make a bigger line change. So also I think now the PTV Visim environment gets stronger also with these line changes, because this is also really important to avoid some critical situations. And overall, we can say with our algorithm, we could reduce really the incidents and also the accidents. So you can see the overall incidents which happens in this 24 hours was 211 accidents, but we could reduce this very much. But also what we could see that we build up different scenarios, and we could have the same level of incidents in all the scenarios. So that was also really important, because this is for what our algorithm is made for. And now I will also mention another project which we started last year. It's a founded project called RELAI, Risk Estimation with Learning AI. So it's a research project founded from the German government, and the aim is here that we can use different data from the simulation, but also from the real driving situations, and we want to generate test scenarios so that we can certificate the autonomous driving functions, which now appears in all the cars which you get new. So it's not only about autonomous driving like a Google car where you can sit in the back. It's also all these functions what we have now in the cars. We have to make sure that these functions are working in the design space, and therefore we are developing, or that's the aim of this research project. And we have here really strong partners involved. So other spin-off from the KIT is IPG Car Maker. It's a simulation environment from this IPG company. So also here it's a really strong partner which also works together with PTV. So these guys are involved in this project, and here we get a really strong simulation environment, but also Fraunhofer Institute from Karlsruhe and Stuttgart are involved. Our partners from Japan are involved, and also the test field of Karlsruhe is involved in this project. And now I figure out a little bit the aim, what we have in the project from the EDI perspective. So I show you already that we already analyzed realistic scenarios. It was a really more manual work. We also could have this incident detector in the simulation. And what we bring in now in RELAI, and already here our approaches on AI-based algorithm are working, that we can find in maybe 30-minute video stream with some information from the car, from the data from the car, we can find critical incidents, and we can also cut this critical incidents like we have it in our incident database. So that is about incident detection, and for sure to evaluate also the system, how good it works. So we are also developing further algorithm to find out which kind of sensors are failing and so on. How our approach works. So we have AI to detect the incidents and also to evaluate these things. And there we can use different kind of data, for sure, video material, but also we could, and that we already did also in Japan, we could use weather information to identify how critical this kind of situation is. And at the end, we can identify the incident, and then we can work on this specific 15-20 seconds, so we can define how much we want to see from this incident. Then we can also label these incidents with AI tools and so on. So that's the next step. And how it works, so as I said, we already have a trained algorithm available, and we have also built some clusters in it so that we understand how critical this incident is. And these different clusters, so that more are for that just an example, we can evaluate in an automatically way the incidents. And if I go back, you could see that we have more than 100,000 of these incidents from Berkeley, and more than 10,000 videos of Waymo. To look to all these videos in a manual way, like the experts from Japan are doing, it would be really hard. And we could use our incident detector, and in this moment, in the way where we calibrate it, we could identify around 1% in the Waymo data and a little bit more than 1.5% in the Berkeley data. And how it looks, for example, that's the Berkeley data set. So you could see we could identify this incident in an automatically way, and for sure it's a clear incident, and that makes us really happy that this algorithm now works also on real data, and so we can support the automotive industry, the suppliers, in finding realistic and critical situations. And based on these situations, we can think, and that is also the aim from RELAI, we can think to more to bring these situations in the simulation environment, and then you could simulate and you could test your system with realistic situations. One other example is from the Waymo. Here we also have we are lucky because they are already labeled in a good way. So here you could see that the pedestrian is walking and crossing the street, and the car has to brake because he expected the pedestrian will run into his car. So that's also about expectation, what the behavior, the people are doing, and also in RELAI, and that's the main focus of our Fraunhofer Institute. They will bring automatically this kind of behavior of the pedestrian into the simulation, so that also in the simulation we have a realistic behavior. For example, if you go to a test bench. Yeah. So to summarize, so we are doing this with a team with 20 people. So we have a lot of data scientists in our team because it's data-driven approaches what we provide for our customers. And we would be also lucky if you join this RELAI project. So if you are interested in this kind of incident detection, if you are interested in realistic scenarios which you can test your systems, then please join also this project. So we also can publish some results then, and you will find also a project page where you can go directly to us. So thank you for your attention, and if you have questions, I will get it.
Great. And it's really nice joint venture. Yeah. So we have some questions from the audience. First one is, did you also look at different behavior of pedestrians?
Yeah, so in the former days with the Japan data set, we get the labels from the experts. So for example, you could get also a label that the pedestrian was drunken, so he was swimming across the street, so that it's really labeled. So here we already look to the behavior, and what we now in RELAI, we want to use more artificial intelligence algorithm, and in this case Fraunhofer is involved to really also make an abstraction level of this behavior of the pedestrian so that we can simulate it. So that's a main focus of this project.
Perfect. We have another one that is, how do you technically analyze the really big data?
Yeah, so that's a good question. So the hardest work is always to prepare the data that you can use it. So also in the case of Japan, I mentioned this database was built up 10 years before. So in the beginning, the hardest work was to prepare all the data that we can use our algorithm, and also with the Waymo data and Berkeley data, and there are some other data. So we are also looking in this MFound project. So it's founded from the Ministerium of Traffic and Digital Infrastructure from Germany. So there are a lot of projects where data are available. So first we have to prepare the data. Then we can look with cluster algorithm if we have a signal-based thing. Or signal-based data, and there is where we are from. So we work since many years, since 12 years. It's also during my PhD, I was working with these time series signals, but also now we are using neural networks to identify objects in the video data and so on. So we make a combination of this algorithm, and also it's one of the approaches automatic machine learning approach, so that we combine different algorithms.
Okay, and we'll have one more, like digging much more into company stuff. Like, how did you get access to Waymo data?
So I'm honest. So our data scientists get this access, but the data set are open. So I think it's possible to download it.
Perfect. So thank you very much for your presentation. Yeah, it's kind of difficult not looking at you on the eyes and looking at the camera to say thank you.
Thank you.
So thank you very much. And now